In the last module, I have shown you the optical nonlinearity or the optical complexity prevailing in the coastal waters by exposing you the spectral signature or the spectral RRS. In this module, let me explain you how did we resolve this issue and how did we resolve this nonlinearity or the complexity, and then finally how did we come out with an algorithm. For that, we have adopted a modeling approach. Let me try to put science into this and explain in a better fashion. So ocean color remote sensing adopt IOP's inherent optical properties. Those in turn are used to compute the shape and or distribution of spectral remote sensing reflectance or spectral signature. And the IOPs themselves are based on particle size, index of refraction, distribution and shape. So if I put everything together in different boxes, we would see that index of refraction, distribution, particle size and properties of all constituents constitute together. You have the inherent optical properties, and then you have the RRS or the remote sensing reflectance. So that means RRS lambda 0 plus means the remote sensing reflectance above the sea surface. So that is what finally passing through the atmosphere, and that is a function of all these optically active constituents and the water molecule, which I have already explained. As I mentioned earlier, to resolve this, we have developed a radiative transfer model, and it is named as Goa University Radiative Transfer Model or GUTRAM. Let me start like this. Ocean color signal sensed by a satellite can be quantified using RRS just above the surface, but that is equal to LU 0 plus divided by ED. LU is radiance leaving the water column and ED is the downwelling radiance, and that is also equal to TWA into TAW divided by n squared W R0 minus by Q, where TWA and TAW are the water-air transmittance and the air-water transmittance, while NW is the real part of the refractive index of water. So far, I have been explaining you the relation between RRS and the light available in that. But then, for modeling, what is required is that we have to develop a relation between the inherent optical properties and the RRS. So next equation explain how this R0 minus and backscattering and A are related. Then further, RRS 0 plus lambda is equal to F lambda divided by Q lambda and the remaining TWA, TAW divided by n squared W into BB by BB plus A, wherein TWA, TAW divided by n squared W is equal to 0.54. BB and A, as you know, these are the inherent optical properties. F by Q is around 0.0949. The remaining, the factors, if you see, F is a complex function of wavelength, water IOPs, solar zenith angle, aerosol optical thickness, and surface roughness. Q lambda is the ratio of upwelling radiance to upwelling radiance, that is U lambda by LU lambda. Both Q and F increases with solar zenith angle. Therefore, F by Q is expressed to be less dependent on solar zenith angle than either of F or Q alone. Hence, you can say, as I mentioned earlier, F by Q is equal to 0.0949 for the sun zenith angle greater than or equal to 20 degrees. Thus, in various bioptical algorithm, RRS to IOP, F by Q is assumed to be constant. Absorption coefficient like A star C, this A star C, A star S and AC dom. A star stands for specific absorption, while AC dom stands for absorption due to C dom. So these things have to be derived spectrophotometrically. Now, finally, what is required? When you develop a model, we need to have an optical closure, wherein you have to see that the simulated or the estimated RRS and the measured RRS has to have a good correlation. So that could be done using this methodology, wherein RRS 0 plus lambda is, you have already seen that LU 0 plus by ED, and it's a function of all the optically active constituents, and wherein LU lambda is upwelling spectral radiance, ED is equal to downwelling spectral irradiance, A is A1 into C1 plus all the other optically active constituents. A1 is specific absorption, A2 is also specific absorption. Let me tell you, in the case of AC dome, we don't have any specific absorption, rather we directly take that because we cannot get the concentration of pseudome. So this way we have modeled and measured one, we are getting an optical closure, and thus we get a model which is calibrated model. The other input for the model are extraterrestrial irradiance on the day of observation, sun, satellite zenith angles and wind speed, of course azimuth difference too, atmospheric pressure, aerosol optical depth, extinction coefficient due to atmospheric water vapor, mixed gases and ozone. Now this picture shows the sensitivity analysis we have done using the model, wherein what has been done here is that we have around 45 stations, and in each 45 stations we have different optically active constituents. We have taken one station where we have the minimum OAC, and then using the model we have estimated water leaving radiance. Of course this is a function of RRS, and that spectral water leaving radiance is taken as the baseline spectrum. Then our aim is, with the change in chlorophyll, how the LW varies, or which part of the wavelength is susceptible for the variation of the chlorophyll. So we have simulated spectral LW for varying chlorophyll concentration, subsequently divided each one by the baseline spectrum, and this is the result. So you can see that for 663 nm, this is a secondary absorption band of chlorophyll, you can see what we get from the model. Similarly at 443 nm also, clearly showing that we have a model which works well, and the sensitivity analysis clearly shows its ability to estimate or the simulate water leaving radiance. Now prior to going for the algorithm which would work irrespective of the turbidity levels, we have developed some site specific algorithms. These are the site specific algorithm for the chlorophyll, for CDOM and TSM. In the case of chlorophyll, this is from estuarine water, and that too this has been developed for the water column during the pre-monsoon period. So for the chlorophyll we have used 670 nm and 550 nm of OCM sensor, while for AC dome we have used 412 and 670 nm, for TSM 490 and 670 nm. You can see that most of these are, the chlorophyll is 5.5931 R1 raised to 0.615, and CDOM 2.93 into R2 raised to minus 2.2, and similarly TSM. Let me tell you that this is a site specific and season specific algorithm, in the sense that if I try to apply this during the post monsoon, if I want to extract or if I want to retrieve this information from the water column during post monsoon season, it doesn't work, it breaks. So this is site specific and season specific. This is the result of the application of that algorithm, wherein this shows the chlorophyll distribution in both the estuaries, this shows the TSM, and this the CDOM. And what is shown on the right hand side is the dynamics prevailing during different seasons. During monsoon season it's a salt wedge estuary, that's what is shown here, and during the post monsoon and then go to the pre-monsoon period, you find that it's a vertically mixed estuary. So the OACs, or the optically active constituents prevailing in the estuary during the pre-monsoon period, could very well explain the kind of dynamics prevailing over there. And this particular algorithm has been developed, again this is site specific algorithm, this has been developed for the northeastern Arabian Sea. And here in this algorithm you can see chlorophyll is a third degree polynomial, and the wavelength used are 670 and 510 nm. TSM we have used 490 and 670 nm. Similar to chlorophyll, this is also a third degree polynomial, while in the case of CDOM we could find that there is a large spatial heterogeneity. In case of inshore water, we have one equation, that is a second degree polynomial, while offshore we have a straight line. So there is a linear relation between this equation and the AC norm 440. So this is the kind of complexity we have seen, and these are the site specific algorithm. So this has been brought here just to explain you that there are number of site specific algorithms prevailing in the coastal waters of the world ocean, but that will not work any other region. As I said earlier, if you have developed an algorithm for pre-monsoon period, that would work only for the pre-monsoon period for that site. It doesn't even work for the next season. With this slide, I come to the last portion of this module, and I would be discussing the detailed methodology adopted for retrieving chlorophyll from the the waters of different turbidity in the next module.